Now that we have a basic understanding of smart pointers, I want to introduce you to the unique pointer. Now the smart pointers are defined in the standard namespace. You can see I do std and the scope resolution operator just to emphasize that. And then for the unique pointer we do unique underscore ptr, and this is a template class, so we do the opening and closing angle brackets. The type parameter t is going to specify the type of the heap object that the smart object will manage. I'll talk more about the declaration and initialization syntax a bit later on through actual examples. And what does the unique refer to? It refers to ownership. The heap object can be managed or owned by only one unique pointer object. The unique pointer object is going to manage heap allocation and deallocation. Right from previous examples, we've seen that we can allocate in the constructor an object on the heap, and in the destructor we can deallocate that again. So in the unique pointer object case destroyed, is going to deallocate the heap object through the pointer that it manages. Since the ownership is unique, the copy constructor and copy assignment operator for the unique pointer object is going to be unavailable. In other words, unique smart pointers cannot be assigned or copied, but they can be moved, and I'll talk about that a bit later. Unique smart pointers are efficient and can be used in most cases where you need to manage a heap object. That is, instead of using a raw pointer. As an illustration, this is what we do not want to do. We do not want two unique pointer objects to manage the same object on the heap. For an example, let's say the uentity pointer A objects would go out of scope, and we would allocate the object on the heap that its member pointer is pointing at in the destructor. Then of course the member pointer of uentity pointer B is going to be dangling. So again, we want to avoid this. The unique pointer does not share its member pointer. We will talk more about how we can avoid errors such as memory leaks and crashes in an upcoming lecture. We basically want each unique pointer object to manage its own heap object, as we can see in this illustration. Now the unique pointer also provides overloaded operators for a familiar workflow, such as the dereference operator and the member selection arrow operator. And note here, smart pointer arithmetic is not supported, so we don't have an overloaded increment or decrement operator. Remember that the unique pointer is implemented as a template class, and that has member functions, such as reset, to deallocate the heap object, and then you can assign a new heap object. We have the getMember function to return the address or pointer of the managed object as well. And as I mentioned in the introduction video, when we use smart pointers, we have to include the memory file. So we'll do #include and memory. We'll start off with a simple example before we move on to an exercise. Now you'll notice that I include the memory file, for the smart pointers. And in the main function, I have this code block or compound statement, and within that, I go and construct this sptr for smart pointer, and that is of type unique ptr, a unique underscore ptr, and I pass in int, and then I use this sort of syntax to construct the object on the heap that this sptr will manage. So I do new int, and of course this integer will be on the heap, right? We have this new keyword, and then we do int right here. This is the object that will be on the heap. So a bit of a different syntax and sort of initialization to what we've seen before. Now before moving on, I'd like to comment out this using namespace at the top here, and if I click here, you will notice that we get a red squiggly. Unique underscore pointer is undefined, and that is because that is defined within the standard namespace. Okay, moving on, in the next statement, you can see I do cout, and I dereference that object similar to how we would dereference a raw pointer. Okay, we do the dereference operator, and then I do the sptr smart pointer. Of course, it doesn't matter what you call that object. This is just an example. You can do uptr for unique pointer as well. In this console output statement, of course, we are fetching that to print that out. So to fetch that, but in this case, in the next statement, we are fetching that, and then we are assigning a new value to that. Okay, so this first console output statement should print out 55, and then this next cout statement should print out 150. When we reach the closing curly bracket over here of that compound statement, that sptr object is going to get destroyed, which is going to deallocate the heap object. Build and run that, and we get 55 and 150 printed out. For a quick exercise, just to get you typing and to get you experimenting with this, go and create an entity struct with an int member and a destructor. The destructor should display an appropriate debug message. Then instantiate a unique pointer to manage an entity on the heap. From here, you want to practice reading from or writing to the int member of the entity heap object that the unique pointer object manages. You'll have to think a bit about how you're going to access that int member of the entity object that is on the heap. Go ahead, pause the video and try this exercise. Okay, I'm back, so let's go and create a struct entity now. I'll keep it simple. We have some entity, and that entity has some integer member, and I have a destructor here as well, which is going to print out an appropriate message. So entity destructor invoked, for example, and in main I still have this compound statement, so this code block, and within that, how do I now instantiate a smart pointer which is going to manage an object of type entity on the heap for us? Well, first I need to make sure to include this memory file, and then we do unique pointer. And what type of pointer do we want this unique pointer to manage? Entity. I'll give the unique pointer object a name. In this case, I'll just do entity pointer, and that is going to manage this object on the heap, this entity object right here. And now the question is, how do we access this member that is now on the heap, okay, where we instantiate that object on the heap? If you're trying to reference entity pointer like this will not work. That is because if I hover over here, the operand for that stream insertion operator is now the std, or in other words std ostream. That is for the left hand operand, and for the right hand operand we have a type of entity. So in other words, of course, this is going to return the object itself, but we want to access the member. So instead of doing this and then doing dot, what we can do is we can use the arrow member access operator. Remember, in the previous example, the unique pointer object managed an integer on the heap. That is why we could simply use the dereference operator, because that would actually fetch that integer on the heap. But of course, in this case, we are working with a user-defined type, or in other words, an object, which could have many members. And again, instead of using the referencing followed by the dot operator, we simply use the arrow member selection operator. Okay, so here I can print that out. That should give us 55. Here I can change it, so I go and fetch that member, which will return an L value, and then I can assign 150 to that. I print that out again. When we reach the closing curly bracket, the unique pointer object, entity pointer, is going to go out of scope. The destructor for that is going to get called, and because that unique pointer manages this object here on the heap, that will then deallocate that entity object on the heap. Build and run that, and this is the output that we get: 55, 150, and entity destructor invoked. And then following that, I also have this end of program statement for myself at the end here of main. If we take a step back, and I'll comment this out here, I'll add another compound statement, and as a recap, this is how we would create an object. So entity1 is of type entity, and then I initialize it to 55, and then I can do cout entity1.member, and of course, when we reach the closing curly bracket right here, that entity object is going to get destroyed, and it will invoke the destructor. So if I build and run this now, of course we will get 55 printed out and entity destructor invoked, and then we'll get the end of the program. Now I have another compound statement, and within this compound statement I have a pointer to a type entity. Okay, so entity pointer, and I allocate an object on the heap, an entity object which I'm going to pass in 55 for the initialization of that member right here, that integer member, and then I'll simply print that out again. Now if you take a second, you'll notice that there is something missing within this code block, but I'll just build around that in anyway, and we will get 55 printed out, but notice we do not get the destructor. What we have to do is we actually have to deallocate that object on the heap, right? The point of this example is we have to remember to deallocate the objects that are on the heap by doing the delete keyword. Now we get 55 printed out and entity destructor invoked, and end of program. I just wanted to make this comparison. In this compound statement, you can see we use raw pointers. We have this raw pointer entity pointer, which is a pointer to type of entity, and we have to go and allocate an entity on the heap like that. This raw pointer is not managed, and this entity on the heap is also not really managed. It is simply pointed to or pointed at by this entity pointer. Then we can go and use it, and then we can go and deallocate it using delete. Whereas in this code block we are using a unique pointer, and that is an owner that is basically going to own a pointer of type entity, which is going to manage this object on the heap, and we can use it once more, alright, and then we can simply let the owner take care of the deallocation of that heap object. You can see we do not have to do delete like we have to do here. So I just wanted to emphasize that. Before moving on, I'll go and clean up and delete those two compound statements, and we'll focus here on this unique pointer. And in this subsection I want to talk about initialization again, and I want to talk about how we can deallocate a heap object and maybe create a new heap object. Let's start off with initialization. So this is correct, this will work. This is referred to as direct initialization. Now I would like to mention that this sort of initialization will not work. Remember that this is not a raw pointer, this is an object. To the right here we are creating a new entity object on the heap returning the address, and we are trying to store that in this here, so this will not work. Now while we are not concerned with the implementation of the unique pointer, I just wanted to show you that if I go to the definition of that unique pointer, that will take me to the memory file, and you can see here that I'll just scroll down. You will see that the constructor is explicit, alright. We've discussed explicit constructors before. You have to be explicit with your construction. It will not make an implicit conversion. If I go back, it's not going to make an implicit conversion from whatever this returns to this type right here. Let's say we want to change that object on the heap, so we want to deallocate the current one on the heap, and then we want to allocate a new one. We can do that using the reset member function. I would like to note that if you use a reset like this, so if you only do .reset and we don't pass it an argument of a new entity, then it's going to set the pointer that the unique pointer manages to null pointer. So we have to check for that. In this example, all we should get is this console output statement right here. So it should print out 55. Then it should deallocate that object on the heap. The pointer to type of entity that the unique pointer is going to manage will be set to null pointer using this statement right here. So this check is going to fail if entity pointer in this case again is going to be null pointer, so this check is going to fail, and then we won't get these statements computed. Control F5 to build and run. And you can see what I mean. We get 55, entity destructor invoked, and end of program. But what I can do is I can do new entity to construct a new object on the heap and pass it 150 to initialize that member. And for this, I'll comment out this line. Now entity pointer will not be null pointer. Build and run. We get 55 printed out. Using the reset function, it will destroy the currently allocated entity object on the heap, and we will get entity destructor invoked. We also use the reset member function to allocate a new object on the heap. We print out 150, and of course, eventually that will also get deallocated once the unique pointer object goes out of scope. The reset function is used to deallocate the existing object on the heap, but it is also used to allocate a new object on the heap. You cannot simply do this. Let's say instead of doing the reset function, we try and do something like that. This is not going to work because this operator, the assignment operator, basically does not exist for the unique pointer. So if I Control B to build, I'll just go to the error list here and you'll see binary assignment operator, no operator found. Okay, so that assignment operator doesn't work for this. As I mentioned, this reset member function is used for both deallocation. In either case, it's going to deallocate what you have already on the heap, and you can also use it to allocate a new object on the heap. Okay, moving on to the next example, I'll just do a bit of cleanup here. Let's say we want to create another entity pointer. This one I'll make entity pointer 1. Then I'll copy that and paste that right here. Okay, what I'm trying to do now is I'm trying to construct entity pointer 2 and have that be a copy of entity pointer 1. Now, of course, we cannot have that because a unique pointer has a unique ownership. In other words, the pointer that it manages can only be managed by one unique pointer object. So if you try and do something like this and Control B to build, you'll get some weird error attempting to reference a deleted function. Go to the error list and again we'll get attempting to reference a deleted function. Basically, the copy constructor is explicitly deleted for the unique pointers, so we cannot do this. And before moving on, I'd also like to mention that if you do it in this way, without providing a new entity like this, okay, with entity pointer 1, this is simply going to initialize the pointer that the entity pointer 2 now manages to null pointer. So we can actually do something like this. So I'll do entity pointer 2, that will return false. And then I use the logical not, so this is going to be true. And then I'm going to print out entity pointer 2 is null pointer. So in other words, the entity pointer that it manages is going to be set to null pointer. I'll just build and run that so we see what we get. And that string prints out entity pointer 2 is null pointer. Moving on to the next example. Getting back to assignment, we talked about the copy constructor. Now in this case, the entity pointer 2 is already constructed, so we want to do assignment now, right? Now in this case, this function is also going to be explicitly deleted. If I build now, I'll just go to the error list. You'll see the assignment operator attempting to reference a deleted function. Alright, some weird error, but basically we cannot use this assignment operator in this way. We cannot assign entity pointer 1 to entity pointer 2. But what can we do? Let's say we do not want to deallocate this entity on the heap. We simply want to move ownership or management of that object on the heap from entity pointer 1 to entity pointer 2. Well, we can use a move function for that. I'll move that line up. Now the pointer that entity pointer 2 manages should no longer be null pointer. Okay, so this should not print out. It should print out this statement. It should do console output entity pointer 2 member, so it should print out 55. And actually, just for fun, I'll do another one of these. Because we move ownership of the heap object from entity pointer 1 to entity pointer 2, entity pointer 1 is now going to be null pointer. In other words, the entity pointer that it manages is going to be null pointer, right? Change that string. Just make sure the string prints out correctly down here. Okay, so it prints out 55, and then it prints out entity pointer 1 is null pointer. Also notice another important thing is entity destruct invoked only gets printed out once. That is because the heap object was moved. It was not deallocated and sort of reallocated. Management of that was simply moved from the entity pointer 1 object to the entity pointer 2 object. Okay, we talked about move semantics in a previous lesson. Let's look at an illustration of this, the transfer of ownership between two unique pointer instances. On the stack I have a uEntity pointer A now, and that's going to point to a heap object. For reference, I have the statement where I declare and initialize uEntity pointer A. Next, let's say we construct this uEntity pointer B. That does not manage an object on the heap currently. In the next statement, we use the move function to transfer ownership of the heap object from uEntity pointer A to uEntity pointer B. Okay, so uEntity pointer B will now manage the deallocation of that heap object. I would like to mention that you don't have to do it in a separate statement like this. You can, I'll just cut this out, cut that out, and paste that between the braces like that. And typically we'd see the move function qualified to the standard namespace because that is defined within the standard namespace. But of course, again, we have it up here, right? Build and run once more and you can see that still works fine. The point with this example is when it comes to unique pointers, only one unique pointer object can manage the heap object. In other words, you cannot have multiple unique pointer objects manage the same heap object, or in other words, manage a pointer that points to the same heap object. As we've seen, this is accomplished by not allowing the usage of the assignment operator nor the copy constructor. As a bonus, again, if I right click on the unique pointer and I go to the definition in the memory file, and you can see here we have the definition. So I'll scroll down a bit, and down here you can see both the copy constructor and the copy assignment operator have been explicitly deleted. Okay, and of course that is why we get those function explicitly deleted errors when we try and use those. Close that off. Moving on with a couple more examples I mentioned that you can do. Entity pointer 2.reset, for example. Actually, I'll just do it up here since we have this check here. A unique pointer object.reset is going to deallocate the object on the heap. So if I do Control F5 to build and run, the entity destructor is going to get invoked, and then both entity pointer 1 and entity pointer 2, that is the pointers that they manage, will be null pointer. As a quick tip, you can actually set it to null pointer in this way as well. Build and run. That's simply what I wanted to show you here. Now we'll also get entity destruct invoked, and both of those are now null pointer. This statement is not simply going to set the member to null pointer, it's also going to deallocate that heap object. For readability, this may not be the best, so what you can do instead is okay, this is more readable, and this is similar to how you can check for raw pointers as well. And you will see that works fine as well. You may prefer this sort of syntax, it's easier to read. If entity pointer is null pointer, in other words, the pointer that it manages is null pointer, then print this out. Otherwise do this. Okay, and same here. Moving on, I want to show you the get member function of the unique pointer. The smart pointer's get member function is going to return the pointer to the managed object. Now typically you want to avoid using this get function. The whole point of a smart object is to have the object itself manage the pointer. But you can get that address. You do the object name and the get. Okay, this is a member function again. And then I assign that to some raw entity pointer. Get pointer to an entity. And then I can do console output raw entity pointer, and I get the member to print out the value 55. Again, you have to think about what is it going to return when you dereference this. It is basically going to return that object on the heap, right? Then we can do dot member. So instead of doing that, we simply do raw entity pointer, the arrow operator, member. Build and run that. And that prints out 55 just fine. A couple more examples to wrap up this lecture. First off, most of these demonstrations I use this integer member, alright, but of course it can be a function as well. So and I'll actually just delete these two statements now. Now I can do that entity pointer to string and build and run that. And that should print out 55 just fine. Also, let's say we have some function. How can we get the information that we want from the main function into this display function? We can create a parameter entity p, which is a reference to an entity constant. And then we can use it like that. Now maybe you should pause the video for a second and think about what we pass in here as an argument. The formal parameter is a reference to an entity constant. So we have to pass in an entity, alright? Well, remember that we have the overloaded dereference operator. So I dereference this entity pointer object, and that is basically going to return the object on the heap. And that is similar to dereferencing a raw pointer. If I build and run now, again, this works fine, it prints out 55. We don't want to use the get function because that is going to return an address, and of course this is easy to work with as well. We simply have a reference to an entity constant, and we know that we cannot make a change to that reference in that function. Alright, I've covered quite a few things in this lecture. For now, we are going to wrap things up, and we'll continue in the next lecture.